Oh, hey, so welcome back. This is now 2.3. Let me get this going on polynomials. Everything you wanted to know about polynomials, but we're afraid to ask. Okay. Let me change the page color, and we'll get started. Okay, so as usual, Math 1530. Polynomials. Okay, so first a general description, definition. There's no easy way to say it really, so generally you'll see it written out in all of its glory, all of its detail. A sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus all the way down to a sub 2 x squared plus a sub 1 x plus a sub 0. Okay. This particular polynomial in its general form has degree n, and its leading coefficient is a sub n. Okay. So an example of something, let's take a look at an example of something which is a polynomial and then something that's not, right? So example, g of x equals 6x to the 7th plus pi x to the 5th plus 2/3 x. Okay, this guy is polynomial, and it is a polynomial. What else? Its degree is 7. You just look for the highest exponent. In this case, it's 7. And then the leading coefficient is 6. Okay, so don't let that pi kind of distract you. Okay, so let's look at one that's not. This guy is not. It has an x in the downstairs. This is actually called a rational expression. If you were trying to simplify it, I mean, you could like butterfly it and be hopeful that it would turn into a polynomial. Maybe it will, you know. But as soon as you see a negative exponent, so in the first one, 3 x's all over 1x will leave you with 2 x's, right? So you get x squared. The other guy, if you rewrite it using your rules of exponent, would be 3x to the negative 1. You can't have negative exponents, okay? All of the n values have to be counting numbers, okay? They have to be like 1, 2, 3, 4. Some things that maybe you take for granted, like y equals 3x plus 2, the equation of a line. This is a polynomial. Okay, so you've already been working with polynomials considerably, so there's nothing to be afraid of here. Okay, this is nothing new. Okay. Speaking of stuff that's new, maybe smooth and, but this is easy to wrap your brain around. Okay, smooth and continuous. So smooth just means there's no sharp corners. Okay, so something that's not smooth would be like the absolute value function that we've seen. This thing right here, y equals absolute value of x. This is not smooth. Okay, and functions that have that property kind of are annoying for particular reasons later on in math. So we want to note if there are any sharp corners. The other idea is this idea of continuity, continuous. And basically that just means there's no holes. Okay? There's no jumping. No holes or jumps. Intuitively, it just means you could draw the thing without picking up your pen. All right. So again, another example of something that's not continuous, as opposed to being continuous, would be something that has an asymptote. Right. So something that looks like this. So I can't draw it without picking up my pen. Not continuous. Okay, polynomials are all smooth and continuous. Okay, so polynomials are all smooth and continuous. Okay, so good to know. Let's look at the end behavior of polynomials in general. 1, 2, 3, end behavior. Okay. So the way we figured this out is by looking at the leading coefficient. And I claim you can already kind of do this just based off your knowledge of lines and parabolas. So recall working with lines. So if you have something like y equals negative 3x plus 2, the line will be going down. If you have a positive, it'll be going up. So in other words, if the leading coefficient is positive, it'll look like that. If the leading coefficient is negative, it'll look something like that. Right? Okay, and what's the degree of a line, the equation of a line? Let's go back up there and look. The degree of y equals 3x plus 2 is 1. Okay, so you don't see it, but that, just because you don't see it doesn't mean it's not there, right? Okay, the degree is 1. So instead of saying degree 1, we're going to say this is degree odd. Okay, both of these are degree odd cases. Okay. And then the parabola. So we had two cases, either happy face when a was greater than 0, or sad face when a was less than 0. And we're going to call those cases degree even, right? Because parabolas, ax squared plus bx plus c, the degree is 2, so those are even degrees. We can generalize from this. Okay, we can generalize. In general, when a polynomial has a degree that's odd and the leading coefficient is positive, its end behavior will be like this. Okay? It'll go towards negative infinity in that direction. And then it's going to do some rigmarole in here, but then eventually it's going to pop out the top like that. Okay? So maybe, it goes something like this, and it goes like that. Okay. Okay. And then the same for a less than 0. So at the ends, it has the linear type behavior, the equation of a line type behavior. In the middle, I don't know. And it's the same spiel with the evens. Okay? If you have a positive leading coefficient, it'll be happy face at the ends. And it'll do some junk in here and then come out and be happy face. Okay? If it's a negative leading coefficient, it'll be sad face behavior. So down here, and then it'll do something in here, and then it'll jump back down like that. Okay? Okay, that's the idea. So let's look at maybe an example where they throw you a randomly generated polynomial and you have to figure out its end behavior. Okay. So first, what is our leading coefficient? I'll just call it A. Right? So A in this case is 11. It is positive, greater than 0. And then what's the degree? Is it even or odd? Well, the degree is 3, and that is odd. Okay? So it's basically has the behavior of a line going up. Okay, so I can make a little picture. If you're on my test, you'd probably make a little picture, but there. Okay. Let's look at another example. And they like to throw ones like these at you. -2 times x minus 4 squared times x squared minus 25. Okay. In order to figure out the leading term, what you have to do is kind of some clever multiplication. So what I'm going to do is multiply -2 times this x squared times this x squared. And that'll be the leading coefficient, believe it or not. Okay, so in the end, it'll be the a value will be, well, not just the a value, but the leading coefficient, the leading term is -2 times x squared times x squared, right, which will be -2x to the 4th. So the leading coefficient is a, which is -2, which is less than 0, and the degree is 4, which is even. Okay? So we have a sad face parabola type behavior. And so on the ends, it'll do something like that, and then who knows what in between. Right? Okay. What we're after kind of is a quick way to graph these without a calculator, where we'll get the important information. The calculator ain't smart enough to figure out what you want to look at. Okay, it could show you stuff, but it's not going to have any direction. It's not going to, well, this person wants to look at this thing, this person wants to look at this thing. It's not clairvoyant. Okay, so you have to give it directions. In order to give it directions, you got to know how these things behave. Okay. And all of the stuff we're showing you here is basically showing you how these things behave, and it's up to you kind of what you want to zoom in on. So anyway, zeros of polynomials will be kind of the next thing that's important, and ultimately for graphing them, right? And what are zeros? Zeros are basically the roots, the solutions, or the x-intercepts, right? Those are the places where y equals 0. So to find the zeros, you're going to let y equals 0 and solve. Okay, so let's look at an example. We have f of x equals 6x minus x cubed minus x to the 5th. Okay. And with the higher degree, the harder it's going to be for us to kind of factor them and find the answers. So we're going to have to develop more methods in the coming sections for finding zeros. Okay, so anyways, let's look at this. Letting y be 0. I can factor in x out of all three terms, negative x in particular. So negative x, and then we'll have negative 6 plus x squared plus x to the 4th, and then I'm going to rewrite that. X to the 4th plus x squared minus 6. So I can factor it, right? And that has a quadratic form. It's like ax squared plus bx plus c. So I'll have x squared plus something times x squared minus something. I just have to figure out the somethings. So it looks like 3 and 2 with the bigger number positive. Okay. And then I can find the zeros. So you take each part and set them equal to 0. Negative x is 0, so multiply both sides by -1. You get x is 0. X squared plus 3 is 0. So x squared equals -3. We're only looking for real solutions. This one won't have any. This factor won't have any. So no help there. And then the last guy, x squared minus 2 is 0. So x squared is 2. Square root property says x is plus or minus root 2. So we're just getting these 3 zeros in this particular case. And again, we're now back to only caring about real numbers. Okay. One thing that happens sometimes with finding zeros is you'll get multiple zeros. And they call this multiplicity. Okay, so for example, if you have x squared plus 4x plus 4 equals 0 and you're solving this, factor it. So x plus 2 times x plus 2, right, is 0. And you get x equals -2. And then x equals -2. So this thing has multiplicity 2, and they're going to give the variable k for multiplicity. So k equals multiplicity, and in this case it's 2, because there's 2 of them in your factorization. Let's look at another one. Another example, f of x, and this guy's already kind of factored, which makes life easier. X plus 5, and then x plus 2 squared. Right? So if you set it equal to 0, set the parts equal to 0 then. So 3 equals 0, that doesn't give you any help. But I mean, you could then expand it if you want, just to make it more clear as to what the multiplicity is. But that exponent is telling you the multiplicity of this 0 from x plus 2 is going to be 2, right? Anyways, take the parts and set them equal to each other, equal to 0. Well, if you want to set 3 equal to 0, you won't get any help. That's never 0. X plus 5 is 0, so x equals -5. Its multiplicity is 1. It only appears once. Then x plus 2, set that equal to 0, and x equals -2. And because the x plus 2 is there twice, you're going to say it has multiplicity 2. Okay. Why do I care? The multiplicity tells you whether or not the graph of the polynomial goes through the x-axis or ricochets off of it. Okay? So when k is odd, you'll have one of two cases. You'll have either it'll be above the x-axis and then hit that particular 0. So in this case, maybe 3, and then it's going to bounce off. Okay, or it's going to be the other way around, right? It'll be coming in from below. It'll hit the 0 and then bounce down below. If k is even, then it'll go through the x-axis. Okay, so it'll do one of two things. It'll go like this and then hit that and go through, or it'll come from above and hit the x-axis and go through. Okay, whatever, I don't know what the intercepts are. Maybe it's 3 again. Right? Okay. So that's why it's important. It's going to help us ultimately to graph the polynomials. Okay. The bigger the number, the more flat it is. Okay, so just one extra thing. If k is like really, really big, so k is way bigger than 1, that's what that double-headed arrow means, the double inequality, it'll flatten the heck out of it. Okay, so if you have something like x minus 2 to the 5th, where the multiplicity, or x minus 2 to the 5th, the multiplicity is really big, it's going to flatten it out a lot, okay, as opposed to just hitting it and immediately ricocheting off. Okay, one extra tidbit before we get around to actually maybe doing some graphing strategy. Well, two extra tidbits. The first one, the intermediate value theorem, which is kind of a high-powered theorem we have, and we'll see again if you take calculus. Basically, it says if a function is a polynomial, and it has this kind of behavior where it's going through the x. Well, if on one side you have like so let's say here's A, and you have this point f of A, which is below the x-axis, and then at B you have f of B, and this is going to seem stupid, but it's important ultimately. If you have f of B on the other side of the x-axis, you know that it's ultimately going to go through the x-axis eventually. Okay, it has to, because it's a polynomial. Okay, and so that place where it goes through the x-axis will be a 0. Okay, so this point right here, if f is a polynomial and f of A is less than 0, which is less than f of B, then there is a C value such that f of C is equal to 0. That's basically what it's saying. For a long time, people were obsessed with finding zeros of functions, and sometimes they didn't know if that 0 even was there. But if you have an existence formula, it's the difference between looking in a haystack for a needle, knowing the needle is actually in the haystack, versus looking through a haystack for a needle, not knowing that the needle is in the haystack. It's the difference between those two problems. And it's not a fun problem if you don't know the needle is actually in the haystack. It's actually a nightmare. So this helps. It may not be clear why it helps. It's more of a historical leftover from times past that people were really super interested in. Anyways, let's play around with one of these. So you have a polynomial f of x equals x to the fifth minus x cubed minus 1. We want to know if there is a 0 between x equals 1 and x equals 2. So is there a 0 between x equals 1 and x equals 2? Okay, so what you do is evaluate the thing at 1. Okay, so if you put it 1, you get 1 to the fifth is 1 minus 1 cubed is 1 minus 1. 1 minus 1 is 0, minus 1 is minus 1. Then plug in 2. 2 to the fifth, 2 times 4, 8, 16, 32. Minus 8 minus 1 is 23, I believe. Okay, so if you have 1 point on one side of the x-axis and the other point at 2 is way on the other side of the x-axis, you know then for a fact that there must be a 0 in between because f of x is going to have to go through the x-axis. Okay, so hence, by the intermediate value theorem, there exists a C in between x equals 1 and x equals 2 such that f of C is equal to 0. Okay, so you can begin your exhaustive search for that 0. Okay, if that's kind of the thing you got to do. Okay. Now I want to start the graphing strategy. So I'm not sure. Oh, wait, before I get to the graphing, it's turning points. There's the turning point idea. Okay, so as you look at these graphs, you'll note the little humps that they have. Those humps are the turning points. So for example, this has how many turning points? It has, those are the places where it goes from going up to going down. So it has 1, 2, 3, 4, 5 turning points. Okay. Okay, let's look at another. How about this guy? This guy has 1, 2, 3, 4, 5, 6, 7, 8 turning points. I'll just abbreviate that TP. Okay. Okay, so can we tell how many turning points a function, or a polynomial rather, will have just by looking at it? Kind of. So f of x, let's take an example. F of x equals x to the fifth minus x cubed minus 1. Can I tell the number of turning points? Well, yes. The number of turning points will be at most 1 less than the degree. Okay, so if the degree is 5, the number of turning points will be at most 4. Now, it can have less. All right, I don't want to lead you into a false sense of understanding. This is just a maximum value. So it's a helper, you know, it can help you draw the thing at most 4. Okay, so let's get to the graphing strategy, shall we? Let's actually worry now about graphing these things. And they don't have to be perfect. Some people try to make them exact. No. It's really dependent on what your job is mathematically, whether you want it to be super good or super good just in one location, right? So anyways, first we'll figure out the end behavior. Secondly, get your X-intercepts and the multiplicity stuff. X-ints and multiplicity. We're calling the multiplicity k. Then get your y-intercept. Then even and odd symmetry, they talk a little bit about that, even versus odd. And then finally, note the maximum number of turning points. And then hopefully we can graph the thing. Okay, so let's try one or two. Here's an example. F of x is x cubed plus x squared minus 4x minus 4. Okay, so first the end behavior. The leading coefficient is 1, and its degree is odd. The degree is 3, right? So it's odd. So it has that linear behavior going up. It's going to go like that, and then do something crazy, and then go like that. Okay, find the x-intercepts. So you set that function equal to 0. And we can factor it by grouping here. So if you group these two together and factor out an x squared, you'll have x plus 1. And then if you group these two guys, you can factor out a negative 4, and you get another x plus 1. Okay. Then both of these terms, okay, these are both terms of products, both have a factor of x plus 1. So we can go ahead and factor x plus 1 out of both of those, and you'll be left with x squared from the first term, and then you're left with minus 4 from the second term. Okay. And then we could factor x squared minus 4 into x minus 2 times x plus 2. So our zeros will be negative 1, 2, and negative 2. And then note the multiplicity. So the multiplicity here is 1. They're all 1. And if it has odd multiplicity, that means it's going through the x-axis. Okay, so in each case, we should be going through, not bouncing off. Okay, y-intercept. So we let x equal 0. So y will be 0 cubed plus 0 squared minus 4 times 0 minus 4. Should be minus 4. And then even and oddness. Usually you just tell by the polynomial, right? If all the terms have even degrees, then it's even. If all the terms have odd degree, it's odd. And I think if it's a mix, then it's neither. Okay? But you can always check if you're not convinced with that logic by plugging negative x in for x. Right? So if you plug in negative x, negative x cubed plus negative x squared minus 4 times negative x minus 4, which will be negative x cubed plus x squared plus 4x minus 4. And that thing is not the same as the original, and it's not the negative of the original. If you pull out a negative, you'll get x cubed minus x squared minus 4x plus 4, which is not the same thing. So remember, if even, f of negative x equals f of x. If odd, f of negative x equals negative f of x. And this is neither case here. Okay, this is not f of x, clearly. And this thing is not negative f of x. So it's neither. Finally then, the maximum number of turning points is 2. And then we could go ahead and graph the thing. Okay, so negative 4, or 0, negative 4 is the y-intercept. X-intercepts at negative 2, positive 2, and negative 1. End behavior, so it's coming up like this, and then it's going to end up going up like this, and it's going through each intercept to the other side. So it goes through, and it goes down here and hits negative 4, and then it's going to go back up through like that. Let's do one more, and we'll call it quits. So f of x is negative 2 times x minus 4 squared times x squared minus 25. So first, again, get the leading coefficient, and you kind of have to, okay, so it's going to be this times this times this. Okay, so our leading term will be negative 2 times x squared, so negative 2x to the fourth, which tells me a is negative 2, which is less than 0, and the degree is even. Okay, so the end behavior will be a sad face type. Okay. Secondly then, get the x-intercepts. You could read those directly off of the equation. So you'll have x is 4 from the second factor, and it has multiplicity 2 because of that exponent. And then from the third factor, well, maybe it's not clear, but the third factor is x minus 5 times x plus 5. So you'll have x is negative 5, which has multiplicity 1, and then x equals positive 5, multiplicity 1. Okay, so I'm saying you could rewrite this as negative 2 times x minus 4 times x minus 4. So 4 has multiplicity 2, and then x squared minus 25 is x minus 5, x plus 5. For the y-intercept, you're letting x be 0, so y is negative 2 times 0 minus 4 squared times 0 squared minus 25. So y is negative 2 times 16 times negative 25, which is some big number, 800. Okay. Then the even odd question, we can plug in negative x and see if we get the same thing back. 2 times negative x minus 4 squared times negative x squared minus 25. That'll be negative 2 times this negative x minus 4 squared times x squared minus 25. So it looks similar, but it's not, right? It's not the same thing. It's also not the negative of the original. If you try to factor out maybe a negative here from the inside of this thing, okay. What would end up happening is that would be, and this would be a plus. So it would still be different. There's just no way to make it into f of x or negative f of x. So it's just not going to pan out. In this case, it's neither. Okay. Lastly, then, the number of turning points. Because it's degree 4, there'll be 3 turning points maximum. Okay, let's go ahead and try to graph this thing now, given all the information we have. So on the x-axis, we have negative 5, 5, and 4. 4, 5, negative 5, 5, 5, and 4. So these guys. We have something way up at 800. So let's just cheat a little and say this is 800 up here. So that's the y-intercept. And then the behavior, it's coming in this direction, and it's coming out, it's a sad face behavior. Right? At negative 5, its multiplicity is odd, so it'll go straight through it, and then it'll shoot up and go through the y-intercept. It's going to come down to here. The multiplicity at 4 is even, so it's going to hit it and bounce off. And then it's going to go through the last one because its multiplicity is odd. And so it goes up. Let's make this smooth, right? So it's a smooth curve. And that gives us an idea that's workable. Okay, we'll leave it at that. Hopefully I didn't rush too much in the video. I apologize if I did. And thanks for watching, and we'll see you next time.